Hi, today we'll be looking at the radial basis function. Basically, what the radial basis function is a way to interpolate your data when you have sparse data and you want to have a smooth interpolation between those. Let's see how it is done mathematically, because it will be used in several papers when we try to analyze them. So the first thing I will do is, again, import all the libraries I would need. So I will be able to display what I'm doing. And why do we call that radial basis functions? It's basically because we have a function that only depends on the distance between the point I'm trying to interpolate and all the points I have inside of my data. So I will have examples, a bunch of examples, and I try to interpolate in betweens. And the only thing that I'm interested in is the distance between the point I have and all my examples to try to find the interpolated values. So that's why we said that it's the radial functions. And it's only depending on the distance, so the points I'm looking at compared to all the points I have. And then we will go through a kernel. So instead of just having the linear distance, you could pass that through any type of function. There is a lot of different kernels, and one of the most used is the Gaussian kernel that I will call phi in this case. And the Gaussian is basically the exponential of minus epsilon r squared, r being the distance itself, and epsilon is how much I want to make that bell curve short or big. Before going through all the maths, I will just show you basically what I'm talking about. So I get the Gaussian, so that's the Gauss, see the exponential functions as we have here. And I will basically call one example function, so I would know what are the functions, and I will just pick a few points around that function, and I will display the function. So basically what I have is this. I have a ground truth, and the ground truth is my red dots. And then I get a bunch of points that I have for which I have the values. So that would be the points I would have truly measured something in the real world. And I need to be able to interpolate, basically to redraw that red curves without knowing what was the functions before, just by knowing the points I have here. So that's the point of the radial basis functions interpolations. And how we will do this, as I said, it's going through the Gaussians. Basically, the functions is here. So the function to find any x value will be the sum of all the distances I will have between my points and all the example I have, multiplied by weights. And then we'll have to do some stuff. So let's see what happens if I just try to do that sum. So to represent what I have here, I've kept all the points that I had in my function. So that's all the points I had here. I have all those points. And then I will draw one Gaussian through each of the points. So you can see that I get the blue one right there, it's at the bottom. Then the second one is that yellow, and you get the bell curve, you know, that goes here with the correct points, and then the green one, the red one, and the purple one. And what we do is that we sum all of them to try to find the approximation, the interpolation we want. And if I sum all of those, of course, what I have is this big function that's completely overshooting what I'm trying to interpolate. And what I could do is I can change the Gaussian curve itself to make it, you know, really a small bell curve. And so the approximation, the interpolation here is closer. It doesn't add to be that big, but then you know that now we dip around here, we go down, which is not what we want. So depending on the value of the Gaussian you have, you get an interpolation that is really smooth or really precise, but tends to go down and not working properly. So the purpose of the radial basis functions now is to actually solve this so the interpolation will go through all the points. And to do this, what we have that I haven't used yet is to say that we had a weight that we could use for each point. So basically, for the first point, I have one weight. For the second point, I have a second weight, third weight, fourth weight, and fifth weight. So I get a weight for each of those, so I can add them together, but multiply them by the weights. And now we have to find the weights that make sure that we will go through all the points. And how to do this? Basically, what we do is that we will turn this into a system of equation, because what we could say is that I know that for my first point, for instance, so if I go 0.1 minus 0.1, I know the value where it would be. So I know that that will be the value 1. And for my 0.2 minus 0.2, it has to be at the value of 0.2, and so on and so on. So I know how what the weight should be for each of the points that I know. So basically what I will do is just this. I will compute the distance between every point. So between all the points I minus all the points j. So basically I do for every point, I do the weights for every point. And that gives me a system of equations. So I get the first point minus the first point minus the second point, and so on, multiplied by the first weight, and so on. That gives me my first value. And it's the known values I have. So because it's a system of equation now that is actually squared matrices here, I can just solve this. I can solve for W, and I will know the W I want to use. So let's see how we do this. I will force my epsilon to be 2. So basically like this, fairly smooth. So I force it to be 2. And then I compute my distance. And as I said, is between each point and each point. And the way I'm doing it is just subtracting all the points, but then taking the advantage of the broadcast of NumPy to make sure that it will build a big matrices with all the distance between all the points. So compute all the distance, and then I will just make those distances go through my Gaussian functions, because that's the kernel I want to use, and that will give me my phi. So first is all the distance. So of course you could see in the diagonal the distance is 0, because that's the 0.1 with the 0.1, the 0.2 with 0.2, and so on and so on. And then it's a big symmetric matrix, but basically you get the distance between 0.1 and 2, 0.1 and 3, and so on and so on. And then when I go through the Gaussian, now what I have is the value when I go through the Gaussians, and then now, of course, in diagonal, I get 1s, because at 0.1, I want to be at 0.1, at 0.2, I want to be at 0.2, at 0.3, I want to be at 0.3, and so on. And I get the different sums of all the weights I want to use. And now, as I said, I get, so that's really here, that's this matrix. And now I can solve for my weights. And if I solve my weights, that's the values of all my weights now. So that's the weights for each of my points. So I can use the function we had. Remember, just the sum of all the distances multiplied by the weights. What I will do is that instead of writing this as a sum, I will write this as a matrix multiplication. It's exactly the same stuff. I'm multiplying my points minus 0.1 with the weight 1, my points minus 0.2 with the weight 2, and so on and so on. And if I do this, basically what I have is that I compute the distance now. I will pick randomly the value 0.5. So that's the on the x-axis, I want to know the value of 0.5. So I can 0.5 minus all my points. I can make that go through the Gaussian, and then I can do the multiplication, the matrix multiplication to get the values I will have. Yeah, I haven't displayed it yet, but so that's the value for the 0.05. And the reason why I wrote this as a matrix form and not as a sum, it's because as usual, inside of NumPy, I can compute more than one thing at once. So what I would do is that instead of computing only one values and having only one row here, I can have as many rows as I want, and that gives me as many answers as I want. So what I could do is I could actually compute the distance between all the points I want to do to draw my curves at once and get all the values, and that's what I do here. And now it's allowing me to display this. And what I will have is, again, the red is the ground truth, and the green is the interpolated value. So you could see the interpolation is fairly close. And one thing that we have with radial basis functions by default is that it's really good at interpolation. It's really bad at extrapolation because it has no clue that it should be going up here. There's no data for him to know that it should be going up and so on. So really good at interpolation, really bad at extrapolation. And you could see, so then my green curve, and then the values I've computed for the 0.5 is just here. It's right on the green curve, of course. And that's basically what you do when you hear about radial basis function interpolation. That's it. That's how you compute it. Of course, your weights can be in multidimensional. It doesn't need to be just, like in this case, one dimension, but it's the same principle. Another thing that I wanted to talk about is the polynomial augmentation, because sometime here I get something fairly smooth, and we could guess already just by seeing where the curve would be. So it's really good at interpolating this kind of stuff. But then I can easily find a function that will not have a proper Gaussian radial basis function interpolation. What I had is I wrote a different example. And I've picked a bunch of points on that functions, and then what I've done is all the steps we had before. I computed the distance, solve for my W's, and then try to interpolate using my weights. And you could see that what I have is that red interpolation, and it's just dips to 0. There is no way for him to do the interpolation because the data is way too sparse and it's missing information, let's say, to be able to do a proper interpolation. What I can see visually here, and I could guess, and actually mainly know because of the function I wrote, is this is probably a quadratic. And I can actually try to tell the interpolation that on top of all my Gaussians, I want him to make sure that he tries to find a quadratic function to do that interpolation. So that's what we could do. We could grow the system that we had before with just the matrix of phi and weights. Grow it with a bunch of constraints, and those constraints will be try to find a polynomial. And to do this, what we do is that we add a second term to the functions, and the second term is to say that we have a polynomial basis and a bunch of coefficients for those polynomials. Then I could choose the type of polynomial I'm trying to solve, because what I can see here that it's probably a quadratic, and I know it's a quadratic. I will tell him as a constraint, I want you to find a quadratic polynomial. So I will build a bunch of polynomial bases of degree 2, which give me this matrix. So basically what it says that I have a matrix with first row is always 1, and then I get the values for x, and then I get the value for x squared. So I will have -2 and then 4. Then I do a second row, it will be for x2, which is a bit bigger. I don't remember what the values are, but you see it will be also -150 and then squared, and so on and so on. So you do it for as many degrees you have and for all the x's you have. So basically what I have in my case is this p, right? I get from all the points I had here, the -2 and -1.8, -1.7, 1.8 and 2. Then it turns into this matrix, and then it's 1, -2, 4, 1, -1.8, 3, 24, and so on and so on. So that's the p I would have. And now how do you combine the phi and the polynomial? You turn it into a matrix form that contains all those constraints. And how you do it is basically you will make a matrix that is a bit bigger. And at the top corner, you get the same matrix as the one we had before. Then next to it, we put all the matrix for the p's. Under the other one, we put the transpose of all the matrices for the p's, and then everything else stays just a bunch of zeros. So that matrix, it's written as a matrix, but really this one is a matrix, that one is a matrix, and so on. So you have to make in your head that it's just a matrix that is bigger. And then where we had just the weights, now we have the weights, and then we have the coefficients we want to find for the polynomials. So basically what it means that for all of the values I have here, all the different values, I will try to find for all the x and x, for all the ones, the x and the x squares, I will try to find the same coefficients because they're only one. So I will need to find the coefficients for all the different polynomials that make sure that this looks like a polynomial. And on the solutions there, we have the f, so the values we know, and then under it a bunch of zeros because basically we want to solve for a plus bx plus cx squared equals 0. So that's what you try to do. So we solve for the vector w and c. Let's do this. So I get my extended phi now. So basically, see, it's the same. I started with the distance and the Gaussian, and then I created a new matrix that is bigger with a bunch of zeros, and I've just injected in the right corners the data for phi p and p transpose. And now I can solve the w's. So I get a bunch of w's here, and what you do is that if I reuse that same concept now to interpolate, so for each values I want to look and also build the extended phi and interpolate using the extended phi, then I only take the values that I'm interested in, so not all the zeros I will have at the end, only the extended values. What I have is this interpolations, and then if I render, I get this. So that's interpolations if it finds. So it did find a perfect polynomial to interpolate the points I have here. That's in the theory. That's what I wanted to show you, how you do it before starting to make things a bit more messy. Because what you've done here is basically, I cheated a little. What happened is that I've created a perfect function. I've sampled that function, and I gave that function to the system. What happened really, if you check the values that this one prints, it's a bit maybe abstract to read, but basically it was the weights for all the different Gaussian, and then actually you could see that they're all zeros because they're all exponent minus 16. So basically they're all zeros. And what he found for the coefficient of my polynomial is 0.7, minus 0.15 and 0.35, right? Which are exactly the values I have. And of course, it had no choice to actually find the perfect value for it, because I gave him the perfect point. So it had to find the polynomial, because I gave him all the information to find the polynomial. And everything else, all the Gaussian and all the radial basis functions are useless for it, in this case. So what I will do is that I will make sure that I actually have a bit of noise in the data I will give him. So it's not a perfect polynomial that I give him, and I don't ask him to solve for a perfect polynomial. So what I will do is that I will keep the same x's, sample all those x's, and then I will offset them to say, well, I'm not exactly looking at those values. It's something a bit random. It's not exactly. I've been a bit random here. It will probably look a bit weird, especially this one. We'll see. So now I have something a bit different. What I should have is, of course, my piece that is values. I get my standard, and then I will get my weights. Now I could see that I do have actual weights for my radial basis functions, and I have weights for the polynomial that are not exactly, or not at all, the polynomial I had at the beginning. And if I do the interpolation, I will get something that is still a radial basis function, with the added constraint that we kind of know that extrapolation is a polynomial, a quadratic polynomial. I have a kind of quadratic polynomial in the middle, so it doesn't just drop with no reason. It has the polynomial that is here, and it did its best guess as what the polynomial and the radial basis functions together should give me as a result for interpolations. So that's what radial basis function with extended polynomial is giving you. So I hope you enjoyed this one, and I see you next time when we will start to use radial basis functions in animation papers. See ya.